Welcome back. In the previous lecture, we talked about the different kinds of hazards. So, in this lecture, we shall look at solutions both in software as well as in hardware. So, let's first consider an example. So, let's look at these two instructions. I'm sorry, over here. Uh, so, in this instruction, as you see, the first instruction writes to register R1, and the second instruction reads from register R1. So, there is a RAW dependence, which is a problem in our pipeline. The reason it's a problem is because when instruction 2 needs the data for register R1, instruction 1 would not have written it. So as we have seen in the past few slides, it is necessary to have three instructions between instruction 1 and 2 such that the information flows. So how do we add three instructions? Well, this is where the no-op instruction comes handy. So recall that we had introduced the no-op or the no operation instruction way back in chapter 3. So this was one instruction which does absolutely nothing, but now we see that it has some role to play in the sense that it ensures that a code in a pipeline executes correctly. So let's see how. So when the second instruction is in stage 2, which is in the OF stage, the no-op instruction that is right before it is in the EX stage. The one that is before that is in the MA stage. And the first instruction is done. So which means that when the sub instruction tries to read the value of register R1, it will get the value of register R1 from the register file. This is exactly what we wanted. And one way of achieving this is by adding three instructions between the add instruction and the sub instruction. In this case, the three instructions are no op or no operation instructions. So this ensures that our pipeline works correctly, but this is a bad solution. The reason it's a bad solution is because we are essentially wasting three cycles and we are not doing anything. So a better way would be that if we consider a larger piece of code, we can reorder the code such that the same constraint, such that the same technique can be applied, but we can minimize the number of no-op instructions that are added. So let's consider this piece of code. So we write to register R1, and at the same time, we read from register R1. Similarly, over here, we write to register R8, and we read from register R8. So that's a RAW dependence. And then we again write to register R10, and we read from register R10. Alright, so these are the RAW dependencies that are there. And in a normal pipeline, unless something is done, this code will not be able to execute correctly. As a result, what we do is that we reorder the code. We can do that. So basically, who reorders the code? In principle, the compiler can do that. So the compiler can reorder the code such that there are three instructions between every producer and every consumer instruction. So this can definitely be done. Or let's say the programmer can also do that if, let's say, the code on the left hand side has been written by the programmer, then the programmer can take a look at the code and modify it appropriately. But it is not a good idea to put the onus of ensuring correctness on the programmer. Such kind of transformations should always be done at an automated level, at the level of the compiler. So what we do is that the first instruction is still the add instruction. We write to R1, but what we see is that the third instruction can be brought over here, and we are not violating any dependence because this instruction has a different set of operands, and this instruction has a different set of operands. So we can happily bring this instruction over here. Similarly, we can bring this instruction which writes to R10 over here. No dependencies are violated. After that, we can bring the consuming instruction, which consumes the value of R1 over here, but we still need to add one no-op instruction to ensure that there are three instructions between the producer of R1 and the consumer of R1. Now let's consider the next instruction, which is the producer of R8. We then have this instruction over here, which is the consumer of R8. So we see that there are also three instructions between them, 1, 2, and 3. So essentially this instruction will get the right value of R8 from the register file. After this, we have one more instruction, add R13, R10, and R2. So here again it will get the right value of R10 because there are three instructions between the producer and the consumer. So what we see is that we can have an algorithm which can be implemented and executed by the compiler. So the compiler can reorder the code without affecting the correctness of the program, as we have done here. And it still might be required to insert a few no-ops, but we want to minimize the number of no-ops because a no-op means that nothing is being done in that particular stage. So we should try to minimize it. And there are a lot of algorithms in the literature that try to reorder code by minimizing the number of no-ops that are required to be inserted. Alright, so we have some solution to take care of data hazards. Let's now try to take a look at control hazards. So the trivial solution in this case would be to add two no-op instructions after every branch. So what we have seen is that the control hazard is resolved in the EX stage. So there still might be two instructions in the previous two stages which were fetched incorrectly. So one idea would be that after every branch, we just send two no-op instructions and then send the right instruction, which is the instruction at the branch target or the instruction just after the branch instruction. But here is a better solution. So let us assume that the two instructions fetched after a branch are absolutely valid instructions. So these instructions are said to be in the delay slots of a branch. So the delay slots would essentially, in our case, in our pipeline, be the two cycles after the branch. So let us try to do something. So let's assume that the branch instruction is there in the program at this point. Let us try to bring two instructions before it and insert them after the branch in the delay slots. So in this case, we are not actually paying a performance penalty. The reason being that we still are executing two valid instructions which are independent of the branch. They would have otherwise executed before the branch. So we're just bringing them after the branch. If we do that, what happens is that we don't have to cancel any instructions or insert any no-ops. So we'll not waste any time. So this kind of a branch is called a delayed branch. So let's discuss the idea of delayed branches in some more detail. So let us consider a code snippet of this kind. So here we have a branch to the .foo label and we have two instructions before it, add R1, R2, R3 and add R4, R5, R6. So as we see these two instructions, the two add instructions, are per se independent of the branch, right? So they don't determine the target of the branch, neither the direction of the branch. So what we can do is that we can bring these two instructions to after the branch and envision a processor which treats a branch like a normal instruction and treats the instructions after the branch as normal instructions as well. And a smart compiler essentially moves instructions which are before the branch to instructions that are after the branch. So they will be in the delay slots because when these instructions would be in their IF and OF stages, we would not know the direction or outcome of this branch. So they will still execute and they'll execute correctly. So the compiler's job is to transfer instructions from before the branch to these delay slots. If it cannot find two such valid instructions, then it needs to insert no ops. So hopefully the idea is clear. So the idea here is that we are not wasting any time after the branch. And instead of B, this can be BEQ, BGT, it does not matter. Let's assume it is BEQ. It does not matter because anyway, if the branch is not taken, there is no problem. If the branch is taken, these two instructions would have executed anyway. And they still are executing because they are there in the delay slots. So we realize the direction of the branch only in the EX stage. By that time, these two instructions are there in the pipeline, so they can be allowed to continue. So such kind of a processor which supports delayed branches are, they were there in the earlier days, and these processors are termed as processors that support delayed branches. And the slots after a branch in which you can fetch such kind of instructions are called delay slots. So, where are we right now? We have taken a brief look at pipelining. We have discussed pipeline data path. We have looked at pipeline hazards. Let me go back one more slide. We have also discussed two software methods of fixing problems with pipeline. One of these was reordering code and adding no-op instructions, such that what is the constraint between a producer instruction and a consumer instruction. There are at least three instructions. So we need to ensure that, and that has been done. In the other case, we have assumed the existence of a delayed branching scheme. So in this case, what happens is that when the branch is there in the EX stage, right, let it be any branch instruction. We have already fetched the subsequent two instructions into the OF and IF stages. So now if the branch is taken, these instructions would have been deemed to have fetched incorrectly. So they would be on the wrong path essentially. So instead of touching them, what we can do is we can get two independent instructions before the branch and put them in these delay slots, which is essentially this slot and this slot, right? So we can put them in these delay slots. So since they would have executed anyway, they will still execute and they'll execute correctly. And after the branch's direction has been resolved, we can fetch the right instruction, either from the branch target or the instruction which is just after the branch, which is in this instruction. So this instruction in this case will be fetched. So there is no problem. Correctness is not being hampered. So these are two very common mechanisms, the code reordering and adding no ops, as well as delayed branches are very common mechanisms of solving issues with pipelines. So we shall now look at two solutions in hardware. So one is a pipeline with interlocks and the other is a pipeline with forwarding. So we'll look at these two techniques because this was a software technique. And software is good, but a problem is that the compiler needs to be aware of all the details of the hardware. This is not always possible because it means that for every new kind of pipeline that we need to have a different and separate compiler. And secondly, one kind of code which runs on one processor will not run on another processor. So to alleviate some of these problems, let's assume that the software does not do anything at all and everything is taken care of in the hardware. So let's look. So interlocks is one hardware mechanism for this purpose. So let me just reiterate what I said. So we cannot always trust the compiler to do a very good job and insert no-op instructions correctly. Also, in this, if you are going for software solutions, you are always tying the compiler with hardware, which is not the best idea. We are also exposing details of the hardware, which the hardware manufacturers might not be very keen to do. That's the reason we need a mechanism entirely implemented in hardware. It's called an interlock. So there are two kinds of interlocks. One is a data lock and the other is a branch lock. A data lock basically says that do not allow a consumer instruction to move past the OF stage till it has read the correct values. So basically you stop an instruction in the operand fetch stage till it gets all the correct values. And the implication of this is that essentially you stall the IF and the OF stages. In a branch lock condition, we will never execute instructions which are on the wrong path. Why would instructions be on the wrong path? They will be there in the wrong path because a branch is resolved in the EX stage, and in the IF and OF stage, we'll be fetching the two instructions immediately after the branch. And these instructions might have been fetched incorrectly because a branch might be taken. So we will have to ensure that such kind of instructions are never completely executed. So the hardware needs to ensure that both these conditions hold, and these conditions, the data lock and the branch lock conditions, are together called interlocks. So let's compare the software and hardware approaches. So in terms of portability, software is limited to a specific processor. In hardware approaches, any program can run on any processor irrespective of the nature of the pipeline, which is definitely a plus. In the case of branches, it's possible to have no performance penalty by optimally using delay slots. In the case of a hardware with interlocks, we have to somehow stall the pipeline for 2 cycles in our design. A basic simple design. So this is at least so in this case, this is one positive point and it's a negative point. Through code scheduling, it is possible to eliminate raw hazards. In our case, we need to stall the pipeline, so it's a bad idea. In terms of performance, well, software approaches are highly dependent on the nature of the program. And in terms of a hardware with interlocks, as we have said, a very basic version is expected to be slower than software, but we'll improve it and try to make it faster than software. But let's at least look at the basic idea behind hardware interlocks. So let's take a look at a conceptual look at a pipeline with interlocks. So let's consider an add instruction. So let's just consider two instructions with a read after write dependence between them. So the first instruction writes to register R1 and the second instruction reads from register R1. So there is a read after write or a RAW dependence, RAW hazard. So what we are saying is that we need to stall instruction number 2 at the OS stage for 3 cycles till it gets the right value of R1, which instruction 1 will write. So how do we achieve that? Well, we need to, in a sense, simulate software and hardware. So what we do is that we need to keep sending no-op instructions to the EX stage during these for the next 3 cycles, right? Till R1 gets written and instruction number 2 reads the value of R1. So let's consider an example. So let's consider again the same two instructions, add to R1 and read from R1. So in this case, let's see. So the first instruction enters the pipeline in clock cycle number 1, and then it just proceeds in the pipeline without stalling. So cycle number 2, it enters the OF stage. Cycle number 3, it enters the EX stage. Cycle 4, it enters the MA stage. And cycle 5, it finishes its job and exits the pipeline. So in the pipeline diagram, we see that instruction 2 enters the IF stage in cycle 1, enters the OF stage in cycle number 3. So at this point, an important decision is taken. It is found out that instruction 2 needs register R1, and register R1's value it's not going to get from the register file because instruction 1 is not done yet. So in this case, what we do is that for the next 3 cycles, it waits, right? So it waits in the OF stage. But in cycle number 4, so in cycle number 4, we do not allow instruction 2 to progress to the next stage. We keep it at its current stage, right? So if in the EX stage, we essentially send a no-op instruction, which is called a bubble. A bubble means a no-op, right? So it's nothing. It's the same as a bubble in water, so it essentially means a no-op. So we send a bubble to the EX stage, and the bubble travels along the pipeline, does absolutely nothing, but it travels along the pipeline and it finally exits the pipeline in cycle number 6. Similarly, in cycle 5, we insert a bubble in the EX stage, and that also travels in the pipeline. In cycle 6, we also insert a bubble in the EX stage. It travels in the pipeline. But there is something interesting that happens in cycle number 6. So in cycle 5, we write the value of register R1 to the register file. So in cycle 6, the value of R1 can be read by instruction 2 from the register file. So now it has the value of R1. So in cycle number 7, instruction 2 proceeds to the EX stage, then it subsequently proceeds to the MA stage, and finally in cycle number 9, it finishes its execution in the RW stage. So what we see is that we need to introduce 3 bubbles. 3 bubbles means 3 no-op instructions in the pipeline in the EX stage in cycles 4, 5, and 6. So cycles 4, 5, let me maybe draw an arrow. Cycles 4, 5, and 6. We need to introduce 3 bubbles. And these bubbles just travel along the pipeline. And since they're no-op instructions, they do absolutely nothing. We wait till we so instruction 2 waits in the OF stage until it gets the value of R1, and that's when it proceeds. So one point is noteworthy which has not been shown in this diagram, that in cycle number 3 we fetch, if there was a third instruction, we would fetch it into the IF stage. But since instruction 2 is not moving, instruction 3 will also not move, so it will get stuck in the IF stage. Finally, when there is, this is in this cycle it's still stuck. Finally, when there is some movement and instruction 2 moves to the EX stage, instruction 3 will move to the OF stage and a new instruction will be fetched in the IF stage. So a bubble basically stalls a part of the pipeline, does not allow any new activity to happen in a part of the pipeline. So in this case, in the IF and OF stage, we have not allowed any new activity to happen till the instruction in the OS stage reads the right value and it is able to proceed. So such kind of an approach, this is a data lock interlock, and we have essentially introduced no-ops in the pipeline dynamically, and a no-op in a pipeline is also called a bubble. So let's look at a pipeline bubble in some more detail. A pipeline bubble is pretty much a no-op instruction. And to insert a bubble, what needs to be done is that we need to create a new instruction packet, as was discussed in the last chapter, chapter number 8. So we create a new no-op instruction packet, which basically tells the pipeline stages to do nothing. And we can also keep a designated bubble bit to say that this is a bubble and mark a designated bubble bit in the instruction packet to 1. So as the instruction packet moves across the pipeline stages, the pipeline will be well aware of the fact that this is a bubble and nothing much needs to be done. I mean, nothing needs to be done. So now let's take a look at bubbles in the case of a branch instruction. So in the case of a branch instruction, when delayed branches are not there, right? The way that things work is as follows. So let's assume that we have a conditional branch instruction beq.foo, where if the condition is correct, then we directly branch to the instruction at .foo. So we have two instructions after the branch instruction. So what happens is that once we fetch the first instruction, which is the branch, till it reaches the EX stage, we are really not sure about the direction of a branch. Once it reaches the EX stage, we have already fetched instructions 2 and 3 by this time. So let us assume that the branch is a taken branch and delayed branches are not there. So in this case, what we need to do is that we need to first realize that instructions 2 and 3 are on the wrong path. They should not have been fetched. So dynamically, instruction 2 is converted to a bubble and instruction 3 is converted to a bubble, which basically means that we either mark a bubble bit to be 1 or convert them to a no-op, and they are cancelled in the pipeline. Since in the IF and OF stages they won't have written to the register file or to memory, it is possible to cancel them. So there is no harm in that sense in cancelling them. So what the way we cancel them is that we convert them into bubbles, and then the bubbles move through the pipeline and exit the pipeline. And when we make a determination that instruction 1 is a taken branch, we then fetch the branch target, which is instruction 4, in the fourth cycle. And instruction 4, since it's on the correct path, it continues along the pipeline. Had instruction 1 not been a taken branch, then there was no necessity of doing it, because instructions 2 and 3 would have been on the right path, would have been on the correct path, and they would have continued their execution and gone down the pipeline. So let's talk about control hazards and bubbles. So we now know that an instruction is a branch in the OS stage. So when it reaches the EX stage and the branch is taken, we convert the instructions in IF and OS stages to bubbles. We have to do that. This will ensure the branch lock condition, which was basically that we do not allow any instruction in the wrong path to execute and move down the pipeline. And to ensure the data lock condition, when an instruction reaches the OS stage, we check if it has a read after write kind of conflict with any of the instructions in the EX, MA, and RW stages. If there is no conflict, so conflict in this case means the read after write dependence, nothing needs to be done. Otherwise, we stall the pipeline, the IF and OS stages only, till the correct data is available in the OS stage and we can proceed. Now let's present an algorithm to detect a conflict between two instructions. So a conflict is defined as a read after write kind of dependence. So let's consider instructions A and B, where instruction B is the instruction which comes first and instruction A comes later. So let's go here. Instruction B comes first and instruction A comes later. So the result is, if a conflict exists, if there's a read after write kind of dependence, then we return true, otherwise we return false. So let's start. If A dot opcode means if A's opcode is, so this is the first line. I'll just correct it in the slides, should be indented here. So if A's opcode is a nope, a branch, a BQ, a BGT, and a call, so this essentially means that it does not read from any register, right? So it does not, since it does not read from any register, there cannot be a read after write conflict. So we can happily return false. So false means that there is no conflict. Similarly, if B's opcode is is in this set, a nope, a compare, a store, branch, BQ, BGT, and ret, this means that it does not write to any register, right? So no register is being written to. So as a result, again, a read after write conflict cannot happen. So we return false. If that is not the case, in theory, a read after write conflict can happen. So we need to take a look at the source registers and the destination registers. So let's term src1 as the first source rs1, a dot rs1, and let's term src2 source 2 as the second source register in the rs2 field. So let us make a small correction for the store instruction. If A is a store instruction, then recall that the second source is not the rs2 field, rather is the rd field. So we make this was a special case made for the store instruction. So this is incorporated here in this algorithm. And if A's opcode is equal to ret, then so the return instruction actually reads from the return address register RA. And so we set src1 as RA, right? So recall that these are all the special cases that we had made. One special case for store, one special case for return. So that's the reason, this has further complicated the logic down the pipeline. So now hopefully the readers can realize how important it is to have a simple instruction set. Nevertheless, sometimes special cases do happen, so they need to be taken care of, like in the case of a store where one of the sources comes from the RD register, and in the case of the ret or the return instruction, where one of the sources comes from the RA register. Now, let's uh, see if yeah, so it's possible that not all instructions will have actually both the sources. So let us by default set the variable has source 1 equal to true. So if the instruction A is a not or a move, so recall that in that case, we don't store the source in source 1, so it is actually stored in rs2. So that's the reason we set has source 1 to false. So basically for this, readers need to go to chapter number 3 to find out why this is the case, but that was just our format. So when we had designed the instructions, we had designed them in such a way that the not and move instructions, the register source or the immediate source was actually in rs2, it was not in rs1. Hence, we set the has source 1 flag to false because it does not have the first source. In rs1, there is nothing. Now, let's look at the destination. So, in the destination field, it is by default the RD register is the destination. However, here also one special case needs to be considered. Say if instruction B is a call instruction, then the call instruction writes to the RA, the return address register, the RA register. So the RA register is saved in dest. That is one special case. And then we need to see, after taking a look at the destination, we need to see if the second operand is a register or not for A. So we set again has source 2 to true. The only special case that will come here. So what is the order? We first looked at source 1, then we looked at the destination, then we are looking at source 2. In source 2, the special case that we need to consider is the case of the store instruction. So in the case of a store instruction, uh, well, I'm sorry. The special case that we need to consider is when the second source is an immediate. So since the store instruction was special in the sense it has an immediate as well as a second registered source, we first eliminate this from our condition. Subsequently, if the instruction has an immediate, then it does not have a second source. For example, if we consider add R1, R2, and R3, I'm sorry, not R3, but it should be an immediate. Yeah, let's give it a second immediate operand, add R1, R2, and let's say 3. So in this case, we have a single register source, which is R2, and this is stored in field RS1. We do not have anything stored in field RS2, and we have a single register destination, which is in RD. So this is exactly what this part of the logic is trying to capture. What this part of the logic is trying to say that if the instruction is not a store, which is special, and if a dot I is equal to 1 means it has an immediate operand, then it does not have a second register source, so has src2 is false. So what have we achieved up till now? So up till now we have set the values of src1, which is the first register source, src2, and the value of dest, which is the ID of the destination register. We also have set the values of the Boolean flags has src1. So lot of instructions might not have the first source, then has src2. So particularly instructions with an immediate operand will not have a valid second source register. So all these three fields are pretty much 16-bit, I'm sorry, 4-bit fields because each register requires 4 bits for encoding, and these are Boolean fields, which essentially say if the source 1 exists, if source 2 exists. Now detecting conflicts is very easy. If a certain instruction has its first source, has a valid first source register, and src1 is equal to dest, so this basically means that there is a read after, dest is the write and src1 is the read. So there is a read after write dependency, then we return true, right? So then a dependence exists. Else if has src2 equal to true, which means that the second source exists, and src2 is equal to dest, which means again there is a read after write dependence, then also we return true, which indicates that between instructions B and A, there is a read after write dependence. So let me summarize our discussion in the last two slides. This slide number 48 and slide number 49. So what we are essentially showing is an algorithm to find dependencies between two instructions, between instructions B and A, where A comes after B. And this algorithm needs to be implemented in hardware, not in software. So we need to do a lot of checks, and a hardware circuit needs to be written to implement this algorithm. What complicates our life is the existence of many special cases, which we are realizing now that special cases, in a sense, are a bad thing, but sometimes they're unavoidable. For example, we had made a special case for store where we store the second source in RD. So this introduces an additional if statement over here. We had made return a special case where it writes to a return address register. So that introduces some complexities as well. Similarly, we had to take care of the call instruction also because it writes to the return address register, and we needed to take care of the immediate format as well. If we would have had more formats, this logic would have become far more complicated, but thankfully it's only limited to 2 slides. Then detecting conflicts is easy. If we have a valid first source, we check if the destination of B is the same as the first source of A. And if we have a valid second source, we check if the destination of B is the same as the second source of A. So after this logic, once we have found out that a conflict exists, how do we stall a pipeline? So what we do is that we disable the write functionality of the IFOF register and the program counter PC. So this ensures that it is not overwritten with new data, right? So that helps us installing the pipeline. And to insert a bubble, we write a bubble or a no-op instruction into the OFEX register, which basically ensures, so if this is the OFEX register, OF on one side, EX on the other side, this is the OFEX register. So if we do this, then it ensures. So if we write to the register, it ensures that this value will propagate along the pipeline as well. So what we need to do is that we need to write a no-op instruction into this register. In the next cycle, it will propagate along the pipeline, and in the next register, which is the EXMA register, it will reach that register in the next cycle. So this is the way a bubble propagates, the same way a normal instruction propagates. It's just that a bubble does not have any effect. So let's now slightly update the abridged diagram of the pipeline that we have been using. So recall that this diagram was introduced in the last lecture with only the core parts of the pipeline. So we have now augmented it with data path with interlocks. So what we do over here is that the first thing we do is that we send the contents of all the pipeline registers because they contain all the instructions. So the IF-OF register contains the contents of the instruction that is there in the OF stage. Similarly, the MA-RW register contains the contents of the instructions in the RW stage. So all of their contents are sent to the data lock unit, which finds conflicts. If it detects a conflict, then it sends a stall signal to the fetch unit as well as to the IF-OF register. So this is a stall signal. So the stall signal basically stops the register from accepting any new data, from essentially overwriting its value. And an easy way of implementing the stall signal is to basically have an AND gate where the AND gate will have the clock entering on one side and the NOT of the stall signal entering on the other side. So the stall signal is 0, the output is the clock. If the stall signal is 1, then the output is 0. So if this can be the clock input for the fetch unit as well as the IF-OF unit. So for both of these units, they will stall and no new instruction will be able to enter into them. Simultaneously, we have an additional set of lines that go from the data lock unit to the OFEX register. So they introduce a bubble. So when we want to introduce a bubble, the value in the OFEX register is overwritten with an instruction packet that corresponds to a bubble or a no-op instruction. So this line ensures that, and subsequently the bubble propagates through the pipeline. So as we see, most of the pipeline remains the same. So at the risk of cluttering the diagram, let me draw a big circle. So this was the older pipeline. And to have a data lock unit, we just take inputs from all the stages and we stall the first two stages. And in the EX stage, we can introduce a bubble. So let us now take a look at the branch lock condition. So let's consider the solution, the software only solution, which was to use delay slots. So while using delay slots, interlocks are not required. So pretty much in every pipeline, after a branch instruction, we have a couple of slots in which there is a possibility of wrong path instructions being fetched. So that's the reason what we do is that we pick instructions that are before the branch and move them to these slots such that we don't, instead of executing possibly wrong path instructions, we execute correct instructions. So delay slots are very simple, they don't require hardware solutions. So let's look at a second option. So the second option is that we convert the instructions in the IF and OF stages to bubbles once a branch instruction reaches the EX stage. Why? So the reason is that in the EX stage we make a determination that the branch, whether it's taken or not taken. So what we do is we just cancel the instructions by converting them to bubbles. The instructions in IF and OF stages, right, are cancelled and they are converted to bubbles. Then we start fetching from the next PC. In the case of a In the case when the branch is not taken, the next PC would be the branch instruction plus 4 bytes. And if the branch is taken, then we start fetching from the branch target. So option 2 is not really the best option, as we shall see. So option 3 is a better option. So the option 3 is as follows. So let's assume that if the branch instruction in EX stage is taken, then only we invalidate the instructions in the IF and OF stages and we start fetching from the branch target. So this is basically saying that instead of invalidating and converting instructions into bubbles all the time, that's a bad idea, it's a waste of useful work. So instead, in the EX stage, if the branch is taken, then only the instructions in the IF and OF stage are not valid. So then they can be converted to bubbles and made to flow through the pipeline. However, if the instruction in the EX stage is not taken, then the instructions in the IF and OF stages are correct, right? They should have been correctly fetched, and they are. So no special action needs to be taken, so we do not convert it into bubble. So in this method, we are essentially predicting that the branch is not taken. And we are optimizing for this case. So we are essentially, if the PC of the branch is P, we are fetching the instruction at P plus 4 and we are fetching the instruction at P plus 8. If the branch is not taken, there is no problem. These are valid instructions. However, if the branch is taken, these instructions have to be cancelled, nullified, converted into bubbles, and then made to flow across the pipeline. Let's now take a look at a data pathway in interlocks. So we have our data lock unit here in place. So the addition in this diagram is pretty much the branch lock unit, which is the new unit over here. So the branch lock unit uh, pretty much takes its inputs from the branch unit, which says it just gives a 1-bit input whether the branch is taken or not. And since we have chosen option 3, which means that when a branch is taken, then only we stall. I'm sorry, then only we insert bubbles, right? Convert instructions in the IF and OF stages to bubbles. What happens is, if we decide that the branch is taken, then we send a bubble signal to the IFOF register. So this converts the instruction which is going from the IF stage to the OF stage. This converts the instruction to a bubble. And simultaneously, we also send a bubble signal to the OFEX register such that in the next cycle, the instruction that goes from the OF stage to the EX stage, that also gets converted to a bubble. And we have an OR gate over here because a bubble signal can come from the data lock unit as well, and a bubble signal can come from the branch lock unit. So mind you, the connotation for this is slightly different in the sense that a data lock unit introduces an extra bubble into the pipeline, whereas for a branch lock unit, all that it does is that it basically nullifies the instructions in the IF and OF stages. The way it does that is that it does not actually change the instruction, but for the next cycle, when the instruction in, let's say, the OF stage will flow to the EX stage, instead of sending the original instruction, it sends a no-op. Similarly, for the instruction that's supposed to flow from the IF stage to the OF stage, instead of sending the original instruction, we send a no-op. That's the only difference, no other difference. And the rest of the circuit remains the same. So all that we see is that we have this extra two interlock units, the branch lock and the data lock units, whose job is to ensure that all data hazards and control hazards are taken care of correctly in our pipeline. Now that we have seen interlocks, we'll look at a far more efficient mechanism. So it's not necessary to stall the pipeline. So what was the main idea of interlocks? The main idea of interlocks was pretty much bubble and stall. So it is not necessary to stall the pipeline all the time. We can get a lot of performance, a massive amount of performance, by actually forwarding data between stages. So we can avoid a lot of bubbles in this process, right? So forwarding is a good thing in a sense, it avoids bubbles, right? So we can write here avoids bubbles. So in terms of performance, it's a fantastic idea. So let's look at this. So let us consider this code snippet once again, where we have two instructions. The first instruction generates a value in a register, and the second instruction reads the value. So in this case, the first instruction generates the value for R1, and the second instruction reads the value of R1, so it's the read after write dependence. So what we would do in our older pipeline diagram with bubbles is that we will essentially once instruction 1 enters, sorry, instruction 2 enters the OS stage, we'll make it wait there for 3 additional cycles and introduce 3 bubbles in the pipeline that will flow through the pipeline. So pretty much this entire amount of this entire region covered by bubbles is wasted work. So this is the work that we are losing, right? The efficiency that we are losing because we have bubbles in the pipeline. So what might be a better idea is to have no bubbles at all, but in this case it will lead to wrong results. So let's take a crucial insight from figure B in the previous slides. I'll go back to it. So when does instruction 2 need the value of R1? So instruction 2 needs the value of R1. We have been saying that it needs it in cycle 3 because it will read it off the register file. So we are saying cycle 3 OS stage, but that is exactly speaking not correct. We actually need it in cycle 4, which is the EX stage. So let me go there once again. So we need it in cycle 3 in the sense that we will be reading it off the register file. So we need it in the register file in cycle 3, but we'll not be using it. We'll actually be using it when, if in this case, instruction 2 enters the EX stage, which is in cycle 4, that's when we'll actually be using the value, right? So we'll be reading it in cycle 3, but we'll be using it in cycle 4. So to be technically and factually correct, we need the value of R1. Instruction 2 needs the value of R1 in cycle 4. So when does instruction 1 produce the value of R1? Up till now, we have been maintaining that instruction 1 produces the value of R1 in cycle 5, which is its RW stage. So cycle 5 is when we produce the value of R1 and write it to the register file. But that also is not correct. So the correct answer is at the end of cycle 3, when it finishes its execution, that's when at least the value of R1 is there, even though the register R1 has not been written to yet. So maybe we can use this particular pattern and do something. So what we shall do is that we shall take a look at this diagram once again and realize that in cycle 4, so at the end of cycle 3, the first thing we need to realize for this code snippet is that at the end of cycle 3, the value of R1, which is the result when we add R2 and R3, the result is ready. So in cycle 4 at the beginning, the result is ready. And also in cycle 4, we need the value of R1. So since the value of R1 is present with instruction 1, which is currently in the MA stage, and instruction 2, which is currently in the EX stage, needs the value of R1, we can always connect the producer with the consumer, because if a value is already there in another stage, we can take it from the other stage. So up till now we have not been we have not been discussing this because our only method of information flow across instructions was via the register file. So one instruction wrote something to a register and the other instruction read the contents of the register. But in this case, what we see in cycle 4 especially, that the value of R1 is present with instruction 1 in the MA stage. And at the beginning of cycle 4, instruction 2 needs the value of R1 because it needs to add R2 with it. So since the need is there as well as the value is there, all that we need to do is we need to connect the EX and MA stages with a wire and forward the value of R1 from the MA stage where instruction 1 is there to the EX stage where instruction 2 is there and it needs the value of R1. So this method is called forwarding. This will work. It will not cause any correctness problems in our pipeline. And it will also avoid 3 stalls. It will also avoid 3 bubbles, right? So the bubbles were pretty important issues in terms of the fact that if there's any producer consumer pair, we had to either find 3 other instructions to put between them, or we used to put no ops or insert bubbles using hardware technique. But in this case, none of that is required because we can directly forward the value of R1 from the MA stage to the EX stage as shown in this example. This is called forwarding. Let's look at one more example. Well, it's the same example, it's just we have changed the title. If you see, this was forwarding in general, but there are different kinds of forwarding. So let's look at forwarding from MA to the EX stage, which is again this example. So we are forwarding the value of R1 from instruction 1 to 2, and as I said, doing it is very easy. We just need to add a wire from the MA stage to the EX stage. So the value will go from instruction 1 to 2 in cycle number 4. We can have many more forwarding paths, right? A multitude of forwarding paths can be there. But let's look at certain rules for creating forwarding paths. So one path we already know, that is from MA to EX. But let us look at some more forwarding paths. So what we shall do is that we shall add a forwarding path from a later stage to an earlier stage, like from MA to EX, right? So we always, flow forward in time. So it's always an earlier instruction forwards data to a later instruction. We try to add a forwarding path as late as possible, which means that we will not have a forwarding path of the form EX to OF, right? That is not required. Instead, we'll have a forwarding path between MA to EX. Why is this the case? The reason is that no instruction actually needs the value in the OF stage. In the OF stage, we read the value, but we don't actually use it. That's the reason instead of forwarding from EX to OF, a better idea is that we forward something from MA to EX. Because so we want to forward as late as possible, so we want to forward, in other words, as close as possible to the actual use. So in this case, we see that forwarding any instruction or any value to the OS stage is not the right idea. The reason being that we would not actually use anything in the OS stage. So we would rather allow the instructions to proceed through the pipeline and use and forward at a later point in time. The IF stage is not a part of any forwarding path. That's the next thing. Because, we don't have to, it sort of follows from the second point that no instruction will use any data in IF and OF stage, so it's not required. And also the other thing is we don't have to do it for a very simple reason that the instruction in the IF stage, right? We can either use a later forwarding path and we'll get the data, and if the instruction is in the RW stage, it would have written to the register anyway, and we will be able to read the value when the instruction in the IF stage moves to the OF stage. So let us look at some forwarding paths. So let's first look at a 3-stage forwarding path, which is across 3 stages. So that would be from RW to OF, right? So recall that we don't have to add a forwarding path from MA to IF. It's not required. We just allow both to progress by one stage and we add from RW to OF. So this basically means that if one instruction is writing to a register and simultaneously another instruction is reading from the register, then instead of getting the data from the register file, they'll get it from the forwarding path. So let me maybe write down the stages. It'll become easier to visualize. We are adding one path from RW to OF, and MA to IF is not required because if you allow both instructions to proceed by one stage, we can use this path. So it's a three-stage path because as you can see, the RW stage is three stages ahead of OF. Now let's take a look at a two-stage path. So one is RW to EX. The other can be from MA to OF. But MA to OF is not required because in MA, what would we get? We ideally don't want to, it's sort of our second axiom over here. We want to forward as late as possible. So MA to OF is not required. We can rather use the RW to EX forwarding path because MA would proceed in one cycle to RW and OF would proceed to EX. And so we don't need this path, so that's the reason it's not required. So an intelligent reader can always ask, why did you need this path from RW to OF? Well, the answer is simple because we don't have any stage after RW. So when we reach the EX stage, the producer instruction is out of the pipeline. So it will not be in a position to forward. That's the reason we use the RW to OF forwarding path here. But we need not have a path between MA to OF because we could just allow both to progress by one stage and use the RW to EX path. Similarly, we can have a one cycle, one stage path which is RW to MA. We will see an example of this. We can have MA to EX. We have already seen an example of this. EX to OF is again not required because in the OF stage you don't need any values. You can allow both the instructions to progress by one stage and use the MA to EX forwarding path instead. So to summarize, so we might not be in a position to appreciate these things completely as of now, but gradually over time we will appreciate forwarding much better. So we will have only four forwarding paths in our design. We'll have one path from RW to OF, one from RW to EX, one from RW to MA, and one from MA to EX. So let's take a look at examples. Understanding via examples is always much easier. So let's take a look at the RW to MA forwarding path, right? So let's, in no particular order, let's start taking a look at these forwarding paths. So the RW to MA forwarding path, let me give an example of two instructions. So let's assume we have a load instruction. The load instruction reads from this address 4R2 and it writes to the register R1, and then assume that we have instruction number 2 which is a store instruction which reads the value of register R1 and writes to a memory address. So there is a clear read after write dependence over here where the load instruction is doing a write and the store instruction is doing a read. So it's reading the value of the register and writing it to memory. So in this case, what we see is that in cycle number 5, the load instruction would have already gotten the value from memory. So the value of R1 would be there with it at the beginning of the cycle. Also in cycle number 5, the store instruction would be there in the MA stage, the memory access stage. And in the beginning of cycle number 5, it would actually need the value of register R1. So that is an ideal opportunity for us to forward. So we forward the value from the RW stage to the MA stage, basically from instructions 1 to instruction 2. And this helps us avoid stalls, and it also helps us execute a load and a store back to back. Back to back means in back to back cycles or in consecutive cycles. Alright, let's take a look at the next forwarding path, which is RW to EX. So RW to MA we have seen, let's see RW to EX. So let's have a load instruction, which again reads the value into register R1. Then let's assume a store instruction, which is absolutely independent, so it accesses a different set of registers. And then we have an add instruction that has a RAW dependence with the load instruction, instruction 1. So it reads register R1. Let's again consider cycle number 5, where the load instruction would have completed its load. So the value of R1 would be there with it. And so we don't care about the intervening store instruction because it doesn't have any dependencies. But the add instruction would be there in the EX stage. And that is exactly when it would require the value of R1. Again, this is the ideal case of forwarding because the value of R1 is already there in a later stage. It's there in stage number 5, which is the RW stage. So from RW to EX, we can just connect a set of wires and forward the value between instructions 1 and 3 and thus avoid stalls. Now let's look at the MA to EX forwarding. We have already seen this example twice. And all that needs to be done is that we need to connect a set of wires between the MA stage and the EX stage. And this is mainly useful for forwarding values between ALU instructions like add, subtract, multiply, divide. So as we, and the previous RW to MA and RW to EX forwarding paths are mostly useful when the producing instruction is a load, because the load's value becomes available only in the RW stage, right, after the memory access is done. So that's the reason the load instruction uses those paths. And the ALU instructions mostly use the MA to EX path. Now let's take a look at a long forwarding cycle from the RW, not a cycle but a chain, a three-stage path from RW to OF. So in this case, we load the value into register R1. And again, since RW is involved, we have a load instruction. We have two more intervening instructions which are absolutely independent, so we do not care about them. And then we have a subtract instruction which uses R1, which is the destination of the load, as one of its sources. So let's again consider cycle number 5. So in cycle number 5, instruction 1, the load instruction is done. It has the value of R1 with it. Instructions 2 and 3 are in the middle of the pipeline. And instruction 4, the subtract instruction, is in the OF stage. So my claim is that at this point, instruction 4 does not strictly require the value of R1. But unless we forward it, we'll never be able to forward it or use the right value. The reason is that at this point of time, if instruction 4 tries to read the register file, it will not be able to get the value of R1 because R1 is being simultaneously written. So we never want to have that kind of a situation with a simultaneous read and write for the same register in the register file. So instead, we can use a forwarding path from the RW to the OF stage to get the value of R1. If we do not forward, then in the sixth cycle, instruction 1 is out of the pipeline. So it's not in a position to forward. So it is true that at this point, in instruction 6, in cycle 6, instruction 4 needs the value of R1, right, urgently needs it. but there is nobody to forward it to. That's the reason we forward it early, right? In a sense, we break one of our rules, but we have no choice. So we forward it in cycle number 5 between the RW stage, which has the value, and the OF stage. So in this case also we have successfully helped avoid stalls. So let's look at data hazards with forwarding. So forwarding has eliminated a lot of data hazards, right? A lot. But unfortunately not all. So we are left with one special case. So there is one case which forwarding cannot take care of. This is called the load use hazard. And this is something where forwarding will not be useful. So unfortunately we still have to stall and insert a bubble in the pipeline. So what is this case? The case is when the instruction immediately after a load instruction has a raw dependence, RAW dependence with it. So let's see. Let's consider a load instruction whose destination register is R1 as we have been doing. And let's consider an ALU instruction whose source operand is also R1. So there is a clearly read after write dependence that we see forming over here. So let's look at cycle number 5 when the value of R1 would be available, would just be available with instruction 1. But the sad part is if we consider instruction number 2 in cycle 4, it will be in the EX stage, and at the beginning of cycle 4 is when we need the data, right? Is when we need the value of R1. And unfortunately, we cannot forward, in a sense, backward in time, right? All our forwarding arrows were pretty much in the same column, in the same cycle. So the sad part here is that in the beginning of cycle 4 is when we need the data, and the beginning of cycle 5 is when we actually have the data. So we cannot actually forward the value from cycle 5 to cycle 4, because that would be tantamount to going backwards in time, which is not possible. So that is why forwarding in the case of a load use hazard, which means that there is a load instruction which writes to a destination register and the immediately consecutive instruction reads from it. This load use problem cannot be taken care of in forwarding. That is because when the data is available in the beginning of the MA stage, that is too late. We we should have had the data ready earlier, which is not possible. So as a result, the only solution is that we need to add a bubble in this case and then use a forwarding path. Otherwise, it's not possible. So we will see that at every stage there is a choice of inputs for each functional unit, and we need to design our pipeline in such a way such that we can choose between the default inputs and the forwarded inputs. So certain complexities will be introduced into our small and simple and basic pipeline. So we'll discuss this in the next lecture. So in the next lecture, we'll talk about how to make a processor with forwarding, and then possibly move on to more advanced aspects for design processors that can deal with operating systems, I/O devices, and look at performance aspects as well.